Hello, my name is Jim Dakin, and by way of introduction, I have a lifelong fascination with light. This began possibly in my childhood, where my father taught me photography and darkroom skills. It certainly progressed through my formal education, which culminated with a PhD in physics. And then I had a very long career in the lighting industry. And throughout my life, I have been fascinated with other aspects of light, such as photography. And it's come up quite a bit in my leisure reading. Having said that, my lifelong fascination with light has led to a book, which I'd like to tell you about. So let me go into screen share here. I'm going to push screen share, and I'm going to share a PowerPoint presentation. Share, and I'm going to put that presentation in presentation mode, slideshow mode. Come on, there we go. My book is titled Wrestling with Light, History, Science, and Applications. And the title comes from the notion that we humans have been wrestling with light from the very beginning. We've been wrestling with light to try to better understand it, and we've been wrestling with it to try to put it to better use. And this understanding and use shows up in all of these different areas, each one of which might be a university course or a profession, for instance. And my premise here is that there's a tendency for any one of us to pick one of these areas, let's say photography, and go very, very deep, and not necessarily think about the broader applications of light, which relate to that particular activity. And what I do in my book is to tie all these things together with a number of unifying themes. Certainly one of the themes is applications of light. And then many of these applications involve very specialized materials, for instance, the paints used in art. We have light associated with heat in many cases. We have light that manifests as waves and light that manifests as particles. And then we have color, like the color that's so important in art or photography. We can tie all of these together. So let's go now, and let's go real quickly through the chapters. The first chapter goes from the beginning to around 1600, and it all starts off with the Big Bang 14 billion years ago, when our universe was created with a lot of light and a lot of heat, more light and heat than you could possibly imagine. Sometime after that, the solar system was formed. Then first life appeared on Earth. And then the first form of light that didn't come from the stars and the moon and the sun and so forth was uncontrolled fire about 400 million years ago. And then it took up until about 1 million years ago for our ancestors in Africa to learn how to control fire, which might be the first application of light, controlled fire, light associated with heat. We Homo sapiens evolved sometimes later with our larger brains, and eventually this led to things like oil lamps and then organized or more formal religions that came about 5,000 years ago. And these religions popped up all over the world during the Neolithic period. In Japan, here's the sun goddess Amaterasu emerging from her heavenly rock cave. In England, we have Stonehenge, which served the purpose of keeping track of where the sun was going up and coming down. And then in the Sistine Chapel, we have God in Judeo-Christianity separating light from darkness in the first chapter of Genesis. These early religions, as far as we can tell, no matter where they are in the world, had something to do with heavenly objects and with separating light from darkness and things like that. Let's jump forward to Greek philosophers. Of course, we wouldn't even know about light if we didn't have eyesight. And the Greeks tried to understand how that worked. Empedocles came up with the notion that Aphrodite, a Greek goddess, had made the eye out of earth, air, fire, and water, and then lit the fire, and that the eye sends out light, which comes back with what we see, sort of like we reach out with our eye to see things, or we reach out with our hands to touch things. That's how the Greeks thought about vision. Let's jump forward to the next chapter, where we go from 1600 to 1900 CE. And here we're talking about the development of modern science, in which we form hypotheses, we test those hypotheses with data, we study the data and everything else we know about, and perhaps we revise those hypotheses and keep going around this circle. Okay, hypotheses. One question you might ask is, what's the speed of light? And the Greeks debated this. Some of the Greeks thought it was finite. Aristotle thought it was infinite. Galileo, in around 1600, came up with the revolutionary idea, why don't we just measure it? And he tried a very simple experiment involving people on two hills separated, let's say, a mile apart. And unfortunately, he wasn't able to measure the speed of light because the hills were too close for his equipment. Very soon afterwards, a very clever Dane came up with a scheme that involved the moons of Jupiter and the Earth traveling around the sun. This scheme gave Romer a baseline of 2 times 93 million miles, and Romer actually measured the speed of light and came up with a value pretty close to what we know today. Let's go back to Africa, the Kalahari Desert, Botswana. Here's a rainbow, beautiful rainbow, and we have to assume that our very earliest ancestors in Africa saw these rainbows and marveled at their appearance. Aristotle wrote about the rainbow, but it wasn't until 2,000 years later that Newton pretty much figured out exactly what was going on in the rainbow. 2,000 years. What is light? Newton hypothesized that light was particles. On the other hand, Huygens at the same time hypothesized that it was waves, requiring a medium which he called ether, that the waves traveled on. This was a great debate for several hundred years, whether light was waves or particles. Up until the 1900s, this was unresolved. So let's go to 1860, chapter 4. Maxwell came up with some equations having to do with electricity and magnetism. 1865, with these equations, he was able to show that those equations could produce waves, like this wave here, and that these waves could explain lots of different phenomena. For one thing, they all had the same speed as the speed of light that had been measured. They could explain polarization. They could explain ultraviolet, visible, and infrared. They could explain X-rays that hadn't even been discovered yet. That was Maxwell, and that was a strong stake in the ground for the wave hypothesis. But the debate wasn't over. Max Plonk in 1901 came up with an explanation of black body radiation. As things get warmer and warmer and hotter, why do they radiate more and more? And why does the color change? Well, Max Planck came up with something called Planck's law, which explained it. Here you can see an object at 5,000 degrees Kelvin, 2,000 degrees Kelvin, that radiates over in the infrared to the right of the red. Here you have light at 5,000 degrees Kelvin that emits right in the vicinity of the eye sensitivity. And then if you go up to 10,000 degrees Kelvin, it's more over in the ultraviolet and tapers off in the visible. And it's no coincidence that the sun, which is at about 5,000 degrees Kelvin, emits radiation right in the middle of the eye sensitivity, and of course we evolved to have vision which worked best where the sun radiates the most. Now, Plonk associated the quantization phenomena that's responsible for this side of the curve He associated that with some quantization phenomenon taking place in the emitting material. But Einstein came along soon thereafter with a better explanation, and he eventually convinced Plonk that he was right in his theory of the photoelectric effect, where the light comes in photons, particles that have energy of hc over Planck's constant times the speed of light divided by lambda, the wavelength. Blue photons have more energy than red photons. So now in Planck's law and the explanation of black body radiation, we have light behaving as particles on this side and waves on this side. So we've gradually come around to the view that light can be both particles and waves at the same time. Let's jump forward to the next thing, which is kind of the last chapter in the modern understanding of light. We had quantum mechanics, which could explain atomic structure, but we also had Einstein's special theory of relativity, which said nothing can go faster than the speed of light. And the two weren't quite compatible with each other until Feynman, Schwinger, and Tomaga developed something called quantum electrodynamics. And in quantum electrodynamics, when an electron bounces off of something that's charged, it does so not by making an electric field that interacts with that something else, but rather by exchanging a photon. And this photon can be used as a probe. You can learn about nuclear matter, for instance, by bouncing electrons off of it, which is precisely what was done at the Stanford Linear Accelerator Center in the late 1960s through 1980. And experiments done there, plus a few experiments done elsewhere, went a long way to establishing what we now call the Standard Model. It's sort of like the modern version of Earth, air, fire, and water. The Standard Model has quarks, it's got electrons and muons. It's also got some things called bosons, which are which like the photon, which are intermediaries of force. And I argue that the photon, the particle of light, is the star of the Standard Model for two reasons. First of all, Newton had talked about particles of light several hundred years earlier, and furthermore, the photon, through experiments like these, had helped us to establish the existence of all the rest. With this, light science is pretty much complete. Now let's turn to applications. One of the first modern applications of light was indoor electric lighting, which was cleaner, safer, brighter, easier to control than things like the oil lamp, which hadn't changed much since the Romans. These electric lighting indoors required the light bulb, for sure, Edison's light bulb, but it also required the infrastructure for generating electricity and transmitting that electricity from generation plants to people's houses. And it was Edison who gets a lot of credit for putting all of this in place in the U.S., first in the major cities, but then by the 1950s, it spread out into the rural areas. All of the traditional electric lighting relied on making something hot enough to radiate. Remember our relationship between light and heat? But it also required new materials, high-temperature glasses, high-temperature metals, and seals, and so forth. On the right here, you see a graph. On the bottom is the year, and on the vertical axis is efficiency in lumens per watt. And you can see that Edison's initial electric light bulb with its carbon filament is down here. It took 40 years to get to the modern electric light bulb, which is about 10 times more efficient than Edison's was. The key advances were going from Edison's carbon filament to a tungsten filament, which can run hotter, and then replacing the vacuum in the bulb with nitrogen, which can suppress the evaporation of the tungsten. Very, very important advance, which was just mind-boggling to the people that experienced it, like my grandmother who told me about it. Let's go on to the next chapter here, chapter 7. from about 1980 to the present. In 1993, the p-n junction had been around for a while. P-doped semiconductor, n-doped semiconductor. If you make a sandwich of these materials and push light through in this direction, the p-n junction passes electricity easily, but it also makes light, blue light, in the case of Nakamura's invention in 1993. The importance of blue light is that you can convert blue light to white light with the use of a phosphor. And okay, so now we have a new way of generating white light that does not involve heat. And if you think about LEDs, the electricity generation and distribution are already in place thanks to Edison. The customers and the applications are in place, again, thanks to Edison. And the primary advantage of LEDs are that they can save energy and provide much longer product life. On average, say changing from traditional light sources to LEDs saves about 3/4 of the energy usage, and it also offers significantly longer lifetime, which is why LEDs are gradually replacing traditional electric light sources. Let's jump forward to chapter 8 here, which goes from the beginning to the present, and talk about some biological applications of light. The eye, Empedocles and the Greeks had it all wrong. The eye is sort of like something called a camera obscura, a dark room, which the Romans had. And it was Leonardo da Vinci around 1500 who realized that that's really how the eye works. Here's our dark room. Here's a tiny hole in the wall of the dark room that lets light in, and here's an image formed on the opposite wall of the dark room. The Romans had devices like this for spying on people. The camera, the physical camera that we take pictures with, was based on that Roman camera obscura concept. But the thing that Leonardo realized was that the eye works exactly the same way. Let's talk about photosynthesis. Photosynthesis takes sunlight and water and carbon dioxide to make oxygen and carbohydrates. Of course, all of the food that we eat comes from photosynthesis, either directly or indirectly. Here you have a wheat field growing wheat for our bread or our breakfast cereal or whatever. But actually, the fire that's started out 400 million years ago on Earth was a result of photosynthesis, because the photosynthesis is what filled our atmosphere with oxygen and then created the trees from the carbohydrates that provided the fuel for fires. A completely different aspect of, or biological aspect of light has to do with our daily circadian rhythm, our sleep cycle. And basically, when the sun goes down and it gets dark, the pineal gland starts manufacturing melatonin, which helps us sleep. And then when the sun comes back up, the pineal gland shuts down, we get no more melatonin, and we wake up again. And for a very long time, millions and millions of years, animals have had their daily sleep cycle regulated by the circadian rhythm mechanism. Let's just finally talk about some modern applications of light. These are all things which were unimaginable 100 or 50 years ago. They were certainly unimaginable when I was a kid. And they all are the result of modern science plus engineering plus specialized materials and factories to turn these into products. We have flat panel displays that are so much better than the small black and white CRT displays that I had as a child. We have huge, of course, there are little tiny ones too in our cell phones. We have the LED lighting that I talked about. Now, if you take the LED PN junction and operate it in reverse and turn it into photovoltaic cells, you can make these huge solar energy farms, which are able to convert sunlight into electricity. And there are now places in the world where you can make electricity more cost effectively this way than you can with burning fossil fuels, for instance. We have fiber optics, which are able to transmit data at higher rates than radio waves can. We have these tiny little cameras like the ones in your cell phone that involve digital imaging, which is so much, which can make the high resolution images that we see on these flat panel displays. And then we have lots and lots of different applications of lasers. We see lasers cutting metal here, but lasers, much less powerful ones, are used for eye surgery, if you can imagine that. Maybe some of you have had eye surgery with lasers. The lasers are also used for barcode scanners and checkout counters. The laser is an interesting case because it was anticipated on entirely theoretical grounds from science before the first actual laser came into being. So let's now talk about our concluding themes. First of all, the relationship between scientific understanding and practical implications. Before around 1900, the applications definitely preceded the science. In many cases, they inspired the science. More recently, the science has inspired applications. Having said that, you need more than just science to have these applications. You need engineering to perfect designs, to put to put the science to work. You often need specialized materials, and you need specialized manufacturing processes capable of making these new applications cost effectively. You need these things in addition to the science. The role of religion. I didn't talk about this but I do in the book. Very early on, our ancestors, before written language, for sure, had noticing the wandering stars in the sky and giving them names like Mercury, Venus, Mars, Jupiter, Saturn, names like that. And it wasn't until, and of course, those wandering stars started to have significance in religion, and religions gave them importance. And that importance persisted for quite a while in religions. And it was only until around 1600 that Copernicus came up with the notion that those wandering stars were actually circling the sun, not the Earth, and that the Earth was circling the sun too. And that led to a progression of things, through Kepler and Newton's laws of motion and gravity, and finally Einstein's special theory of relativity. That sequence of events started off with religion, started off with our innate curiosity, but passed through religions and very much fed our modern science through some of the giants that I just mentioned. And you can question whether we would be here today if religions hadn't started all of that going. There's also the interesting question of whether any particular advance can be attributed to an individual celebrity like Edison or to a collective effort. I think quite often the Edisons get too much credit and the collective effort not enough, and we talk about that in the book. There's the premise that the broad story of light cannot be found in any single university course or book, except this one. And I hold to that premise. And I think this book is great. It's an opportunity for an honors seminar or a general education course at a university, which is accessible to students beyond the normal STEM students who are taught about life. And that is possible partly because the topics that we talk about in this book are so broad, and also because the book doesn't have the mathematics, which is often intimidating to non-STEM students. And with that, I'd like to stop sharing and thank you for your attention. and encourage you to buy the book. Thank you.